this, we love it. And the speaker just confirmed that he agrees that it's great if we have a lot of interactivity during this seminar. So please don't be shy. Please don't save your questions for the bitter end. Let us know about any questions, concerns, comments right away, please. You can ask questions in the chat. I mean, there are several ways. There's the Q&A. You can totally use it. For some reason, we usually don't. There is the chat. That is, people tend to use that a lot. If you do, please make sure to send your messages to all panelists and attendees. You get this scroll down menu with options. All panelists and attendees is what will reach everybody. You can also speak, but I think only if you're a panelist. Some seminar attendees are more equal than others. They are known as panelists. And then there are attendees, and they can only listen. However, if you are an attendee that wishes to receive an upgrade, now is the time to speak or send me a message or whatever, and we'll be super happy to upgrade you. I usually don't do upgrades during the seminar because you will lose connectivity for a while before you reconnect. But like anyone of the attendees who would like to become a panelist now, just say the word and we'll be totally happy to do it. Is there anything else I'm supposed to do? And I put all of this in the chat already. Anything else I should say? So this is a Simon's Workshop seminar, and everybody who are registered for the workshop, which most people should be if they're attending this meeting, are welcome to gather at GatherTown after the seminar, and I put that link in the chat also. In a best case scenario, I will remember to repeat it towards the end of the seminar. We will have kind of a two-part seminar this Tuesday, as we usually do. A 40, 50-ish minute first part on quantified Boolean formula solving, QBF solving, and then after a break, 10-minute break, maybe a slightly shorter part on going into things like I think first-order logic and satisfiability modulo theories, SMT, but the speaker will make everything clear in just a minute as soon as I let him start, which I'm about to do now, I guess, unless there's something else, which I don't think. And I think the participant number has now jumped in the customary way and stabilized. So why don't we get going? So it's an immense pleasure today to have with us Mikoláš Janota at the Czech Technical University in Prague. And again, we won't waste time on extolling Mikoláš's CV. We just want to hear him talk about his exciting research again, which has been, I think it's fair to say, focused on automated reasoning in different forms and shapes. In particular, Mikoláš has done a lot of exciting work on QBF solving, and I think he will tell us about some of it today and how to harness the power of machine learning in this space. But all of this is really speculation. Mikoláš will tell us now. Please.
Okay, so hello everyone. So there's these sections, so a little bit of intro on QBF. Some of it you might have heard already from Martina Seidel. So there might be a little bit of overlap, but I think this is kind of necessary to make the talk complete. And then I will say a little bit on my work on solving QBF and how you can use machine learning within QBF. And then in the second part is about how some of these techniques can be lifted to first-order logic. And one context is the finite models, right? So meaning that if you have a first-order logic formula, you want to find a finite model. If there is one, there might not be one. And there you can also try to do machine learning. And the last part is about what I've been doing most recently, which is about applying machine learning in the context of satisfiability modular theories. Also, just to give a little bit of just contextually where I am now. So I've been living in Portugal for many years, and now I moved back to Prague, and I started a research group here at the Technical University of Prague. And the focus is exactly this: the satisfiability modular theories. So, so I'm happy to show some of the works that we've been doing. It's a little bit recent because I moved just a couple of months ago, essentially. But I hope it's interesting. Okay, so yeah, let's get going. So you all know that in SAT we are just asking if a formula is satisfiable or not, and if it is, then we would like to have an assignment for the variables that makes it as satisfiable. In QBF, I still have the same language, but I can also write quantifiers. And since it's finite, I can rewrite the quantifiers into Boolean connectives. So for all is just a conjunction and exist is a disjunction. So if I take a formula, I can completely get rid of the quantified part by rewriting it into these Boolean connectives. So for instance, in this step here, I took the exist y and I rewrote this in a disjunction. Of course, it was at the price that the size of the formula doubled, right? So I need to say either it's true for 0 or it's true for 1. And I can do the same for the the for all by saying a conjunction. So it must be true if x is 1 or x is false. And this actually, after I done all this, well, then I can just get rid of all the connectives. I can simplify to a single constant. So it's obviously decidable, but if I do it like this, the whole formula grows too much, and this is something we would like to avoid in practical solving. Oh yeah, as Jakob said, you can stop me at any time. I'm kind of going through this slightly more accelerated because I'm sure that most of you've seen it, but if some of you haven't, just stop me. Then there is also this relation between QBF and first order logic. So sometimes I present my work to some people that work with first order logic, and they think I'm talking Greek to them or Chinese. And so I like to have this slide that shows that the step going from QBF to first order logic is not that huge. So if, for instance, I have this formula that says that for all u exist e, u if and only if e, right? So these are just Boolean variables that can only be 0 and 1. And this formula, of course, is true because if I set u to 1, then I set e also to 1 and the other way around. And I can rewrite this to first order logic by adding a special predicate that represents truth. So I'm kind of reifying truth. And I have two constants. One represents the truth and the other represents falsity. And I say that truth should always be true and falsity should always not be true, right? So I have these two constants. And then if I want to rewrite this original formula, I just say, well, for whatever value u has, if u is true, then the predicate over u must be true. So I replaced the existential variable with a predicate. So for every existential variable in the original formula, I introduced a predicate. And for every universal variable, I just kind of wrap it in this truth reification. Anyhow, I don't want to go in too much detail. It's those that are familiar with first order logic, so they might recognize that this is the Bernays-Schinfinkel fragment, or sometimes people say EPR, which means that I don't have functions. I have only constants and predicates, which also means that the Urbrand universe is finite. So the details might not be completely crucial if you don't understand them right now, but something to take home is that you can go from QBF to first order logic. So you can translate QBF into first order logic in a rather straightforward fashion. What is a little bit strange is that the original formula was symmetric, right? So there is no particular difference between the quantifiers in the QBF case, but in the first order case, somehow all of a sudden they are treated differently. This is something that's been puzzling me for a long time. I don't think there's any good answer to that. And another annoying thing is that the EPR fragment is decidable. So it's a decidable fragment of first order logic, but the complexity of this fragment is different than QBF. So QBF is p-space and Bernays-Schinfinkel is a next time complete. Okay, so this one nice relation between QBF and first order logic. Then, of course, we
Mikoláš,
can. Yeah.
I guess you already told us that we shouldn't worry too much, but let me just quickly worry, and then you'll tell me that I shouldn't maybe. But if you go back, so like, is there any reason for me to think about how would a disjunctive clause be translated that mixes universal and existential variables, or we should just move on and ignore this question?
Oh no, this is I think that should be easy to answer, right? So I'm not even assuming conjunctive normal form. I mean, I'm just, so this is, even I could, right? So here I have this can be thought of as two clauses, right? But I have an if and only if.
Mm-hmm.
So I'm not assuming CNF. And then, so each of the literals that you have in the propositional case, you replace it with a literal. So it's a mapping between literals to literals, right?
Okay.
And the universal ones, they're wrapped in this truth thing. So because the existential variables, they stop being variables, they become predicates, and the universal variables are still variables, but they need to be wrapped in this truth because I cannot use a variable as a term.
But I could think of this as like a literal by literal syntactic replacement, and the overall
it's a
structure of the
completely
formula will be exactly the same.
Yeah.
Okay, got it.
Yeah. So there's the question. So the transformation QBF is strictly included in EPR. Yes. Well, I mean, of course, the language is different, right? But the step of moving from QBF to a subset of EPR is fairly easy. Yeah. Then there's the question: isn't P E like a Skolem function? Yeah. This is the same idea. Yeah. So this PE behaves like a Skolem function. It's essentially the same idea. There's something about Ibner universal. Oh, sorry, inner variables. I was afraid that you're asking about Ibner variables, and I didn't know what they were. So you're asking about inner universal variables. I don't think there is an issue. So I mean, the quantifier prefix is the same. You just remove. Well, oh, okay. So maybe if you're familiar with Skolemization, as was said here, right? So it's kind of the same process, right? So in the end, I have only universal quantifiers, and the existentials, they're just predicates that have in their arguments the predicates that are before the original existential. Yeah, well, anyhow, I mean, this is more of a side remark that so this is not so much the target of the talk, but it's a nice relation. So okay, so let me move on. So just a little bit of background. So SMT, I'm sure that most of you have heard of SMT, and I'm not going into any technical details about SMT. We're just assuming that there are some theories like natural numbers or reals or functions that we can reason about. So besides the standard first order logic semantics, we also have the semantics of the theory that is being considered. So for instance, in this example, I'm saying that I have a function, and I don't know what the function is. It is a function, and we call such functions uninterpreted functions because we don't know what their interpretation is. We have to find it if there is one. And I'm saying that for whatever x, which is a natural number, fx has to give a positive value. And additionally, I say that if that f of 0 is negative, right? So this is a contradictory formula because if it's supposed to, if f is supposed to be positive everywhere but supposed to be negative on 0, that's a contradiction. So this is not particularly difficult to see. Of course, I can have more complex examples. So for instance, I'm saying that f is increasing, right? So I'm going, if I go from fx to fx plus 1, I have to go up. And then I'm saying that I decrease every 100 steps, right? So it's a kind of a strange property, right? So it's increasing every step and then decreasing every 100 steps. And if you think about it, that's also contradictory, but it's not so obvious. Obviously, I have to know that the comparison, so less than and greater than, they are transitive, and I have to know something about plus and etc. So this is oh yes, Philippe is saying it's Esker stairs. Yeah, it's true. It's exactly that. That's a good name for this formula. Also, I mean, as a fun exercise is to think about if you replace here 100 with a positive constant, right? So if you say it's decreasing every c steps, and c is some positive constant. I don't know which one. And if that's the case, that I think you need induction to prove this, and this is typically out of reach for nowadays solvers. I'm not gonna talk at all about induction, but just to show what are some of the peculiarities that might appear. Okay, so we have QBF and a relation to first order logic. We have SMT, which is kind of an extension of first order logic to specific theories. And there is also this nice relation that I really like to use, that between QBF and two-player games. So what we imagine is that we have two players, the for all player and the existential player. And the for all player is trying to make the formula false, and the existential is trying to make the formula true. And they're giving values to the variables according to the quantifier prefix, right? So they're alternating based on what is written in the quantifier prefix, and they either give 0 or 1 to each of the variables. And a QBF is false if and only if there exists a winning strategy for the universal player, and it's true if and only if there exists a winning strategy for the existential player. which also means that we don't have stalemates. So there's always a winning strategy for one of the players, either of the players. So for instance, this formula is true because, well, one point of view is that I just expand, right? So I plug in these Boolean connectives, and that was a lot of work because we had to expand everything. Or I can think about the game, and the game is what? The existential is waiting for what the universal is going to play, and it's going to play exactly the same value. And it's always going to win because they just need to be equal. Right? So this is a kind of a nice example how it's useful to think about these quantifiers as two-player games, because I can reason very quickly why this formula is true. Okay, so this is a bit of background. So there's a lot of work on solving QBF, and I'm going to mainly talk about what I've been doing. You've heard from Martina about the other approaches, I'm sure. So one observation is that we can write the universal quantifier as a conjunction. Well, so if I have universal variables here in the inner quantifier, so I'm saying exist, some existential variables for all, some universal variables, and some formula phi. I can get rid of the universals by writing a conjunction by going over all the combinations of the inner quantifier, the inner variables. And now I don't have QBF anymore because I have just one quantifier, which is called SAT. Right? So if I have exist and bunch of variables and no more quantifiers, this is exactly the same as solving SAT. So this is good news because I don't need a QBF solver. I can just run a SAT solver, and SAT solvers are very good. The issue here is that the expansion is too big, right? So maybe SAT solvers are very good, but it might happen that I'm not even able to construct the expansion because I need to consider all the values for the inner variables, and there might be just too many. So there is this nice idea that instead of expanding all the values, so all the bit vectors that might give value to the inner variables here, I will try just some, and that sometimes helps, right? So well, I don't know. Maybe I could try some audience participation. So I have this QBF formula. And I'm claiming that I don't need to consider all values for the inner quantifier, but I only need two possibilities of the three variables. Anyone has a suggestion? Or maybe I can ask a simpler question. So if we think about the two-player game, right? So I claim this formula is false, meaning that whatever value is given to X, the universal quantifier can respond with something that falsifies the formula. So let's say X is false. What should the universal player play to make it false?
Play all them true.
Yeah.
Than W.
Yeah. So if the X is set to false, the universal player just sets everything to true here, and that will force falsity, and it falsifies everything because there's a conjunction here. And obviously here it's symmetric. I just need to play all false if X is true. Yeah, so this means that the universal player really needed only two types of moves, either play everything true or play everything false, depending what the value of X is. So if I plug in these two values, instead of these 2 to the power of 3 possible values, if I plug only these two, I will get one implies X and one implies not X, which really simplifies to false. Now the tricky part is, what is a good expansion, right? So what are the good moves of the inner quantifier that that we should consider? And there's this nice idea that we can do this gradually using this counterexample guided abstraction refinement, which sounds very fancy, but it's really just this idea that we try to play something and the opponent beats us with a counter move, and we prepare ourselves for the opponent. We prepare ourselves not to be beaten again by the same counter move, right? So we're kind of collecting the counter moves that we have been beaten with until we find a move that cannot be beaten, or we just know that there is no move for the outer quantifier. Yeah, so what is roughly what is going on? I pick a value for the outer quantifier, right? So I'm still talking about this case where I just have two levels of quantifiers, but this can be generalized. So I pick the first value, and I check by running a SAT solver if this can be falsified, meaning that the universal player can win. If that's the case, we have a counter move, and we need to prepare ourselves for this counter move. So we don't want to be beaten ever again by this counter move, meaning that we should be able to satisfy the formula if the opponent played this counter move that just beaten us. Yeah, and this gives us a new candidate move. And again, we check if this can be beaten, and if yes, we get a counter move, and we plug it in, and we're saying, well, you have to be able to win if either of those counter moves is played in the second round. Yeah, and we repeat this process until either we find a move that cannot be beaten, or this conjunction becomes unsatisfiable. Yeah, and if you think about this, what is happening is that we're gradually expanding this conjunction. So originally we said the universal quantifier can be rewritten as a huge conjunction, but rather than doing that, we're just doing it one by one. Any questions here so far?
How would I know? I mean, n is potentially exponential here. So
Of
after
course,
a while,
yes.
I might start to worry that I'm not making much progress. But I would usually n doesn't grow too large, or there's a good way of figuring out whether we're making progress.
Yeah, so that's a good question. So I guess the short answer is that as long as the polynomial hierarchy doesn't collapse, we don't have too much hope that we can bound this n, right? Because if n is small, then I have small number of SAT calls for a problem in the second level of polynomial hierarchy. So theoretically speaking, right, it's unlikely that we will ever have algorithms that will be able to somehow bound this number of SAT calls.
No, that's clear. But even for formula, we're aiming to solve formulas that are easy in some sense, right?
Yeah,
but
sure.
Even for easy formulas, this could be like a terrible approach, or it could be genius. or somewhere in between?
Yeah. It could be both. So actually, this is what I'm gonna talk about next. So yes. So yeah, let me get to that. Just a quick recap. What is nice about this algorithm? You can write this really fairly easily in we're just using 2 sat calls in each loop, right? So this is not very difficult to implement. So if you have only 2 quantifier levels, you have to worry a little bit about the fact that you're manipulating these formulas, which might potentially not be CNF. And so you need the formula and the disjunction, and the negation. So you need to introduce Satan variables if you're using a CNF SAT solvers in the end. But again, so this is not particularly hard to implement. Just a side remark: the original algorithm is non-CNF, right? So this has some advantages because CNF is known to bring in some problems for QBF, and it can also be generalized to arbitrary number of levels, and this is essentially done by recursion. So this algorithm is doing exactly the same, but instead of calling SAT solver again, it calls itself in the lower levels. And it can also be generalized to non-CNF. Sorry, not pre-X. Anyhow, okay. So let me get to what Jakob was asking about. So what are the good and the bad and the ugly cases of this algorithm? So what is nice is that it can stop early. So imagine this situation that we have exists and bunch of variables for all y and some other variables, they don't matter, and some formula that says that phi and y should be true at the same time. And we don't know what phi is, but it doesn't matter because as long as I set y to false, everything is false, right? So it doesn't matter what's the rest, but I can win this very easily by just saying y is false. Yeah, so this is the nice case when we just plug in a value and everything stops right away. You can do something similar for truth, right? So if I have something like x or phi, and again, if x is true, then the whole thing is true, and it doesn't matter what the rest is. And so again, this is something that stops right away. Now, what is happening is when what is bad, and I will get to this in more detail, but essentially the idea is that if for every candidate move I have a different counter move, right? So I'm essentially not learning from the previous counter moves because I need always a different counter move. So this is kind of a vague description of the problem. So imagine you have something like this. So you're saying exists x such that for all y they are equal. Well, this is not true, right? Because again, from the perspective of the game, if x is true, y is false. If x is false, y is true, right? So they just play the opposite, and the universal always wins by falsifying the equality here. However, if I do the expansion, I really need these two values. Right? So this doesn't look very good, right? Because this is a very simple formula, and I really need to see that y can be true and false. Right? So I need two iterations for this formula. And as you know, things grow exponentially very easily. I can just make it ugly by putting a disjunction between a bunch of formulas of the same type. They are completely independent. And maybe I could detect that with some pre-processing, but of course that's beyond the point. What is happening is that I'm saying, well, find me a vector of variables x1, x2, such that for any vector of the y variables, at least one of these equalities is true. And the response is, well, it's not possible because, again, the universal plays exactly the opposite, right? So it mirrors the, it plays the negation of this, and it falsifies all the disjunctions. Okay, so we need all these 4 values of y1 and y2.
Mikoláš, there's
yes.
been a question in the chat for a while.
Oh yeah. Wouldn't the partials in step 6 be useful? This is something that, okay, so this is something that we were looking at also. This has been very annoying. Well, not very annoying, but it's something that is counterintuitive. So there is no good way of using partial assignments without going into much detail, or at least I haven't figured out really how that would work. So you're plugging, essentially you're alternating the 2 players. So like if I go into this more intuitive notion of 2-player games, and if I plug in only a partial move of one of the players, I'm just making it easier for the other one rather than making it more difficult. Yeah. So I mean, I don't know if that's, it's if it's a sufficient answer, but I've never figured out a good way how partial moves would be helpful. At the beginning, I also thought there might be a way of doing that, but yeah. Yeah. Okay. So this brings me to this part, which is about machine learning in QBF, and it's motivated by exactly this problem, that I have a bit vector. So I'm looking for a bit vector that certainly doesn't exist. We already know that, but the solver doesn't. So I'm looking for a bit vector, so a sequence of Boolean variables, so that for any other bit vector, at least one of the bits is the same. Yeah. So I'm saying find a bit vector so that for any other bit vector, at least one of the bits is the same. And we know that this is not possible, but this problem has this annoying property that for whatever bit vector I consider for the first part, there is one that makes all these disjunctions false, and it's exactly one. So it's the one that plays the opposite, right? So I flip all the values of the variables, and none of the disjunctions is satisfied, but is exactly one that is violating it. And so there is this sort of a I probably wouldn't say paradox, but something that's been, I think, nagging the QBF community is that I have a formula that is fairly easy to see why it's false, meaning that there is a small strategy for the universal player or for either of the players, doesn't matter. But if I run the solver, it's going to need a lot of time. So in particular, it will just expand all the possibilities. So this is exactly the case which Jakob was pointing out. In the worst case, I'm expanding exponentially many times. And here I'm doing exactly exponentially many times. I'm doing exactly the full number of expansions. But it's strange because there is easy response, right? So if I know that the universal player plays the opposite, I can just plug in this value and everything falsifies, right? It simplifies to false. So if I plug in, instead of zeros and ones, if I plug in the negation of the x's, everything becomes false. But where do I get these functions? So rather than plugging in constants, I want to plug in functions. In this case, it's a negation of the particular variable. But where do I get them? Right. So this is the hard question. And what I did, I tried to use machine learning for exactly this, and it's a little bit different approach of machine learning than what we're usually used to. So typically we use machine learning to give some sort of guidance or classification, but here we really need the object. So we're trying to learn an object that will represent the function. So we're still playing this game of candidates and counter moves. So we just go back and forth. And the idea is to observe some sort of a pattern in the counter moves. And we observe this pattern by running machine learning for each of the individual variables. And then if we have the pattern, or we hope that we have the right pattern, we plug it into the formula instead of these constants 0 and 1. So this is roughly the idea, and we can repeat. And just to show on this example, so so this would be the sequence of games that I'm playing. So I have these 2 move games. So I played 0 0 0 0, and the response was 1 1 1 1 1. So it's always playing the negation. And then I see, well, 0 0 0 didn't work, so I will flip the first bit. And the opponent also flips the first bit and again wins, and I repeat and repeat and repeat. And eventually, if I run some machine learning algorithm, it will figure out that the response for the universal is the negation of the existential, right? And we repeat this and we plug that in, and it really works. Now, how it is exactly done? Well, not exactly, but it's roughly done in the implementation. So I do the loop as you have seen before. I still do recursion to have multiple levels. I still do the refinement, meaning I plug in the values and functions. And I don't run learning all the time. I just run it every k steps. And the k is maybe like 32 or 16. I tried different versions. It's not too much, so it's a little bit of atypical learning, because in typical machine learning you have many data points. Here I have just a few data points. And now what I'm using to learn is decision trees. And why do I use decision trees? Because they give me an object that I can pick up and plug into the formula back again. So if I used a neural network, it wouldn't be any use to me, because I cannot take a neural network and write it into the QBF. Or maybe I could with a lot of effort, but it would make the QBF harder to solve than it was before. A side remark, there is this additional heuristic that I really needed, was that if I learned already some function in the previous iterations, I kept it as long as it was working. So I call this don't fix what ain't broke. So if you learn something and it's working, don't try to relearn. Any questions here? just a little bit of results. So this is already 2018. So at the time I was very excited because I tried a bunch of different things in QBF, and this was really the first time I was getting some improvement. It's maybe
question. So this is like, is this specific to? I guess you did two QBFs so far.
Oh yeah, so I do this. I do this.
Is it more like a generic?
It's just so it works for multiple levels by recursion.
Okay.
Yeah, so I didn't want to really get into the recursive part. It gets a little bit more technical, but the whole algorithm is implemented for arbitrary number of levels. Having said that, these algorithms don't seem to work very well for many levels. So if you have 3 levels, I think it's fine. If more, then maybe a different solver might be better.
But it could happen when you say don't fix what ain't broke. It could be that your strategy function like keeps coming up with good counter moves to the, I guess, for all ansat player, and then you'll just let this function play for a while.
Well, it's a little bit tricky because you have these multiple variables, and you have a separate function for each variable. Oh. So the strategies are changing. It's just those that seem to work, I'm keeping them, right? So I mean, if I go back to this example, for instance, if I look at the first 2 samples, here I see that yn, the last variable, is always true. So any reasonable machine learning algorithm just says, well, then just play always true, right? So don't invent anything. I mean, if it's always true, just play always true, right? But then in the next step, I already see, oh, it's false here. So I need to reflect that.
So there are a number of questions in the chat now that are accumulating that we should read out because they won't be visible in the video recording posted on YouTube. But if you could read them and answer them.
Yeah. What happens if the function you learn is wrong, meaning that once you see more of the truth assignments, the learn function is invalidated? Yeah, so the good answer is there's no wrong answers. So there's no wrong functions. And what does it mean? So this boils down basically to this idea that it's a universal quantifier, right? So if I have a formula that says, well, exist, where's some formula? If I have a formula exist for all, an arbitrary formula, not necessarily this one, but if I have an exist for all formula, something like this, the existential value has to work for whatever the u variable happens to be, right? So whatever the function is for you, the e has to be right. Yeah. So I mean, from complexity point of view, and I probably should make this remark, is there is something a little bit strange, right? Because so I can solve this by plugging in all possible constant vectors of u. So this will grow exponentially. So I can convert to SAT by converting to an exponentially large formula. But if I'm trying functions, all of a sudden the space is double exponential, right? Because the number of functions is much larger. So this is this is a little bit strange. However, it's still the case that whatever strategy the second player is doing, it must work, right? So the first player must play something that beats any possible strategy. Hopefully that answers the question. Oh, there's one more question. What guarantees that these learned functions are simple, smaller? Well, nothing. We're just hoping that, that the learning algorithm will learn a small tree. In my case, it's a decision tree. And this is kind of the aim of machine learning, right? To have small explanations. But of course, there's no guarantee. There could be easily some threshold, so I could decide not to use the learn function if it looks too complicated, but I haven't done that. That would be easy to do. Then there is a question. This is really synthesis of Erbrand functions, counterparts of const function, isn't it? Yes. This is a synthesis of Erbrand functions or Skolem functions, depending on the quantifier. So this is completely symmetric with respect to the quantifiers. So you can either see it as synthesis of Skolem or Erbrand functions. It doesn't really matter in QBF. Okay, let me go. Yeah, so I think there's been some good questions. Now I have the second part on finite models, and maybe it's a good time to do a break. I'm not sure what time it is exactly. Is it too soon?
No, this is an excellent time. It's 25 minutes past the hour. So I guess let's just say that if there are any other questions, we can take them now, and as soon as we're done with any outstanding questions, we'll take a 10-minute break. If there are any questions from anyone, yeah, Thomas, please.
Very nice talk. Could you please say a little bit more about the problems with the CNF in QBF? I think you don't only refer to the Zeiten transform, because then you don't know which variable, a new variable would be on which existential level, and what are all the problems? Could you say a little bit more?
Yeah, I don't have any slides on that, but essentially so maybe there's different responses to that. So one thing is the level, you're right. So I have to decide at which level I'm going to put the existential variables. And of course, you can always put them all the way to the end, which might not be a good idea. So we actually have some small paper with Olaf Beiersdorf, and that shows that if you move them all the way to the end, it might be much worse than bringing them more to the left if you can, right? So they always have to appear to the right of the variables that they are kind of represent. Anyhow, so yeah, this is just one thing, but roughly speaking, I think the intuition here is that if you give the solver the Zeiten variables, the solver doesn't know that they are Zeiten variables. So when you construct the Zeiten variable, you know exactly what the interpretation should be, right? So let's say you have a Zeiten variable that represents a conjunction. So you know what's the strategy for that variable. Play the conjunction of the two literals that are represented by that Zeiten variable. But the solver doesn't know that, right? So it has to somehow figure it out on its own, and it might not be able to, it might be just a lot of work to actually do that. So I mean, of course you could try to do it syntactically, so you can go and, oh, actually this was probably a Zeiten variable, so maybe I should, but then so why did someone make it into CNF if someone has to go and go back, right? So I mean, this is a bit of ungrateful line of work to reverse engineer near the encoding. Another issue that is very visible in the algorithm here. So you need the formula and its negation, right? So you need both. F and the negation of F. Now, if you have a formula, and so if you start with a non-CNF formula, bring it into CNF via Satan transformation, as it is equisatisfiable, which doesn't mean it's equivalent, right? So if you give me an equisatisfiable formula using the Satan transformation, and I go and I negate that, no longer it holds that double negation cancels itself out, right? Yeah, I mean, if you think about it, right? So imagine you take a non-CNF, you bring it into CNF by Satan, and somebody gives that to you, and you negate. Well, how do you negate? You bring in a new set of Satan variables to negate the CNF, and in fact, you should be able to get the same formula because you negate it twice, but it's not the case. Yeah, hopefully that that clarifies the to a degree. Yes, yeah. There's two papers. There's actually an older paper. One is called Achilles heel of, and I forgot of what. Also, and I have another paper which is called Achilles heel of term resolution. And they both talk about this issue of CNF version.
Okay, thank you.
There's one more question in the chat.
Oh yeah, the synthesis. Yeah, that would probably be interesting. The synthesis compared to synthesis. I think it depends a lot on the benchmark. So my impression is that it will probably not work so well because the QBF problems are typically rather large. So you have a large number of variables and the formula is large. It's a bit of also a chicken and egg problem. So I know that there's been work on using QBF within synthesis, right? So Markus Rabe has worked on this. So I feel like there might be some sort of a chicken and egg problem. Yeah, but it would probably make sense to look at this. I mean, there is related to this is that in SMT, Andrew Reynolds has work within CVC4. So CVC4 is an SMT solver, and he's using the SMT solver to synthesize things, and it's kind of based on some similar ideas that I've been using in QBF. So I think he calls it synthesis by refutation or something like this. And again, so it's there is and so he's been doing a lot of work on this. So there is definitely this relation, and on top of that, a bit of a chicken and egg problem that it feels like you could use the solvers to do synthesis, and maybe you could use synthesis to improve the solvers. Yeah, there's definitely more work to be done here.
Okay, thanks. So let's take a 10-minute break starting now, and then we'll be back to talk about finite model theory, right?
Yeah.
Perfect. So I think that we are preparing to resume in about a minute or so. If people have had time to grab their coffee or, morning coffee, evening coffee, midnight coffee, early morning coffee, depending on where on the globe you are.
Yeah, I try to avoid drinking coffee at this time of the day.
Yeah. But we should ask Supratik about that. Yeah.
I'm happy to have tea. I'm in the same time zone as Supratik. Not coffee, but tea is fine.
Okay. Even this time of day?
Yeah, anytime. I'll have it at midnight also. It's not yet midnight here.
It would have, what is this called? Like rooibos or something? I could do that, but nothing stronger than that.
Red Bush.
Red Bush, yeah.
Yeah.
Okay, so let's see. Have we, what should we do? Have a tea discussion, coffee discussion, or should we perhaps, one suggestion could be to let Mikoláš continue. I could quickly organize a poll on this, or maybe I'll just stop blathering and say that we're back from the break. And Mikoláš, it's all yours again, please.
Okay, so this kind of closes the chapter on QBF, and now I'm kind of getting more into this kind of more exploratory stuff. So one thing that I tried was using or applying the same ideas in the context of finite model finding. And why should this work? Well, we can imagine this finite model finding as a kind of a higher order quantifier, right? So instead of looking for some Boolean variables, we are asking, are there predicates and functions that will satisfy our formula for whatever the value of the universal variables are in that formula? And if it's finite, then maybe it's not so far from QBF, because the predicates can still be written finitely, right? So they're large, they're much larger, because if I want to write like a truth table or for a function I need like a multiplication table, they're much larger, but they're still finite if I'm just looking for finite models. So I can try the same trick. So first I don't assume anything, and then I find some interpretation for this empty assumption. So I find an arbitrary assumption, interpretation. If there is no interpretation, I stop. In this case, in the first round, that's impossible. And then I test if the interpretation that I just got, whether it's a good one, right? So I have some interpretation for my predicates and for my functions that are unknown, and I check if it's a good one. If not, I have some value for the universal quantified variables that negates the model, right? So the interpretation, well, the interpretation is not a model of the formula. And we say, well, you have a counterexample. We have to be able to find an interpretation for the predicates and the functions so that it is able to deal with this particular value of the universal variables. So again, it's this same idea. It's just that the two players are a little bit asymmetric. So I still have existential and universal, but the existential is playing over predicates and functions, and the universal is playing over the first order variables.
Sorry for a stupid question. What is alpha here, and like where does?
Oh yeah, this is like my approximation of the formula. So if it's getting gradually strengthened.
Mm-hmm.
right? So if so, this is still the same story, right? Because I'm in finite domain, because I'm interested in finite models. If I plug all possible values for x's, alpha will be just a conjunction over all these combinations.
Mm-hmm.
Yeah, and I'm looking for and then it's essentially an EPR problem, right? Because once you get rid of the first order logic variables, you only have predicates and functions and constants.
I guess what I'm not seeing is, are you setting them somewhere at the outset? Is that like, so I guess I'm missing something, but is this part of
Yeah,
alpha,
this is, sorry. So I just kind of, I just kind of wanted to keep this short and a little bit informal, but yes, the way this is written is unclear. Yes, so you're right. So I'm gradually strengthening the problem. So again, I have a fixed value for the first order logic variables. I plug them in,
sure,
and I add that to alpha.
Okay.
So alpha is just growing.
And then capital I, or fancy style I should think of
It's an interpretation.
Okay.
It's an interpretation. So so alpha is like an EPR problem essentially. It's like it's not it's infinite. It's a finite model problem where I don't have any variables, any first order logic variables.
Mm-hmm.
Right. So I have
I is like what you'll be playing for the P's and the F's.
Exactly. No? Yeah. Exactly. Yeah.
Okay.
Yeah. Exactly. Yeah. Yeah. So this I is what you're playing for the interpretation for the first player.
And then in line 4, the for all player gets a new chance.
Yeah. Yeah. Yeah.
Okay. Okay, got it. Thanks. Yeah, I was just confused. Sorry.
Yeah. No. I just this is still the same idea. It's just that instead of
makes perfect sense. Thanks for explaining. Yeah.
Okay. So actually I forgot to expand. So actually it's here. So sorry. So the line was there. I just forgot to hit page down. Yeah. So the alpha is being strengthened the whole time. Okay. So again, we have this, essentially it's a grounding, right? So I'm doing this grounding that is going one by one, and the strange thing about this grounding is that I have an interpretations for P's and F, but only in the points that I have grounded so far.
So this is probably answering a question in the chat, whether this I is like a partial interpretation then.
Yeah, exactly. Yeah. Exactly.
And then other listeners are worrying about whether we are inside EPR still or outside.
Yeah. Yes. It's essentially EPR. Yeah. I mean, I'm kind of hesitant to say it's exactly EPR because I have functions, but since it's finite model, they're not real functions, right? Because they have a finite range. So I could rewrite each function as a bunch of predicates that would encode the value of the function. If that answers the from a complexity point. Yeah, I mean, it's obviously not directly a SAT problem because you have predicates and functions, but there's no variables, it's just constants. And I think the complexity
half
is
of the people asking approve of this answer. So
yeah.
I think we can continue.
Yeah, no, but I think Daniel has conceded. I think he's agreeing now.
Now we have a 100% buy-in, so you can definitely continue. Yeah.
And I think the complexity of this is known to be the same as next time complete. So yeah, so we get this partial interpretation on the existing ground terms, but so we don't necessarily know what's the interpretation for the whole domain. So imagine that someone gives you, let's say, a truth table that is partially filled in, and you're trying to figure out what's the rest. So that not necessarily is clear, and obviously you have many options. Probably, typically, double exponential number of options how to do that, because the grounding will be small because you need to keep it in memory, and you just construct it one by one. So I think this is a kind of a more general problem that goes beyond this finite model finding. It also appears in SMT. So this is kind of why I got interested in this problem, because it's a kind of a step between QBF and SMT, but essentially these kind of issues remain everywhere. So typically what happens in SMT solvers is they just assume some sort of a default, right? So you know that your function should be return 3 if the argument is 4, and should return 3 if the argument is 3. And then we don't know the rest, so it just puts some sort of a default like 0. And then you might not be able to find ever the interpretation, because you're just looking at some small portions of the truth table. So rather than doing that, I was interested in learning the rest, right? So again, you have a partially filled in truth table or a multiplication table, and you're wondering whether you can just extrapolate to the rest. So rather than just filling in a default everywhere, you just put some learned value. So you look at what you have so far and you try to learn from that. So here is kind of an example where this would work, and essentially it's the same thing as this bit vector that I had in QBF. It's obviously syntactically not the same thing, but in some sense a similar idea. So I'm saying there's some predicate with n variables, and I'm saying that the predicate should be true if and only if the first variable is equal to some constant t. And of course, I mean, if I look at this, I know, well, this is actually a definition. This is not even a problem. I can get rid of it. But of course, I can hide this kind of semantics in something that the solver cannot detect. So if I ground all the x variables in the argument as 0, and if I flip the first one to 1 and the rest to 0, I can learn from that the predicate should be true if and only if t is 0, right? So this is how it happens. So I say, well, p over all zeros should be true if and only if t is 0. So there's no learning here. I'm just plugging in the values of x's, and here I'm plugging the value of x's with 1 and all zeros, and now the right-hand side changed. But this is just substitution. There's no magic here. So we know that this should be true, and I do this partial interpretation of p, and well, t, I don't know. Let's say t is 1. We don't know what it should be. It doesn't really matter for us. And then I say, well, p of all zeros should be false, and p1 of all zeros should be true. So again, so for p, I have just 2 lines of the truth table defined, all zeros and 1 and all zeros. And I can learn from this because, oh, actually this just depends on the first variable. So I fill in the rest of the truth table by just looking at the first variable. And in this case, this will work, right? Sorry. Yeah, okay. I should say something about the results. I didn't put any results I could have had. So the results were a little bit ambivalent. So I should probably admit to that. So I mean, you know, this expansion somehow was typically beaten by just expanding everything. So I was looking at some benchmarks from TPTP, which is a library of first-order logic problems, and somehow like this very careful expansion going one by one just didn't pay off. Like it because typically you have these small clauses with few variables. It just paid off to expand everything. So in this finite model finding, using these finite domains, I'm sure, you know, there will be some cases where this paid off, but it didn't pay off for me. However, I think these ideas still translate to some other domains. So I mean, this is something that I still have as one of the targets to have some sort of learning like this for more complicated domains. Yeah, any questions here? Oh yeah, there is. How can I get the slides and list of the cited references? Yeah, I can upload that. Yeah, just maybe Jakob, if I forget, bother me, or
Yeah, I guess, or you like choose your favorite search engine to Google Mikoláš Janota and use email. Worst
yes,
case.
you can. Yeah, that's the worst case. Yes. No, but yes.
I
Yeah,
don't
I mean,
know if Simon posts slides online. I'm actually not sure about that.
I mean, these slides are just reside currently on my computer, right? So
Yeah.
unless I put them anywhere, they won't be anywhere.
Okay.
Okay.
Well, take that as homework.
Yeah. Okay. So and yeah. So as Jakob was advertising at the beginning, so this part of the talk is going to be much shorter. So this I'm getting to the final part, and this is kind of work in progress, but yeah, so I kind of I have this problem that I always like to talk about the stuff that I'm working on now. So you know, some of it is maybe a little bit half baked, but hopefully interesting. So okay, so like now we want to move to general SMT. So again, we have some first order logic problem with the theories, and one thing that we kind of rely on in SMT with regards to quantifiers is this famous Erbrand's theorem, which I'm sure many of you know. If you don't know, it's not terribly complicated. So the intuition is that if I have a quantified formula and then it's unsatisfiable if and only if I can ground it with terms, with finitely many terms, and make it unsatisfiable. Yeah. So so to give an example, so I have this formula that says that f is an identity, so fx always return x. So this is a quantified part of the formula. And then I say, well, if I apply f twice to some constant c, it should be different from c. And now obviously this cannot be true because f always returns the same. But of course, in order to prove that, I need to know what equality means and what a quantifier means, etc., and functions and stuff like that. But I say that I can get rid of the quantifiers by instantiating the quantifier with finitely many terms. And in this particular case, I plug in C, right? So if I plug in C instead of x, I get that f of c is equal to c. And then I plug in f of c into x, and I get f of c is equal to fc, right? So now I have the original ground statement that was saying that applying f twice to c is different from c. And then I have two statements that I derived from the universal quantifier. Sometimes people refer to these as lemmas. And they say, well, if you apply to f to c, I get exactly the same. And if I apply f twice to c, I get the same thing as applying f to c. But we already know that applying f to c is equal to c, and this gives a contradiction here, right? So using then some sort of equality reasoning, I already get a contradiction, and I don't have to worry about quantifiers. So this looks kind of nice, because I'm saying essentially the take home message is, well, I don't need to worry about quantifiers as long as I know what values I should plug into the quantified variables. And of course, that's the hard part, because I don't know which values I should plug in. But if I know, then things become easy in quotes.
At a high level, what this is saying is sort of if the formula isn't true, then I can always find a finite counterexample.
Yeah.
Or is it saying like more than that, or?
A little bit more than it's not really a counterexample, because you need to plug in. You might need to plug in multiple, right? So like for x, I need to plug in two different terms for x. It's not exactly a counterexample, but I can do a grounding. Maybe let's say grounding. I have a finite grounding that, and then okay, in the context of SMT, there is something that sometimes people refer to as like an improved Herbrand's theorem, which is saying essentially the same thing, is that I only need to look at the terms that are in the formula. However, the catch is that the formula is growing. So what do I mean? So imagine that you have some quantified part of the formula and some ground part. So the G has no quantifiers. And I look at the part that has no quantifiers, and I look for all the ground terms that I have there, and I pick one and I plug it into X, right? And I get another ground part of the formula, right? So I get this lemma, right? So I pick some term from G, and I add it to my ground part. So now my ground part is larger because I instantiated the quantifier. Now my pool of terms that I can pick to plug into X is growing. So it's a kind of an onion structure. So initially I can only plug in things that come from G. And in the second step, I can pick anything that comes from G and the lemma that comes from substituting T1 into X. Yeah, and I continue like this. So I'm getting these levels of terms. So initially I have only the terms in G, and then I have the terms that come from the substitutions, and I'm picking those. So in the end, the set of possible substitutions is infinite because it keeps growing. But in each step, I'm looking at a finite number of terms. So algorithmically, this is nice, right? So I don't need to pick a term that just comes out of the blue. I'm just looking at the terms that are in the formula right now, and I don't need to worry about the rest. And it's known to be complete. Yeah. So this is this improved Herbrand's theorem. So this is nice. I should say there is an issue if I have theories. So this works if I have no theories, so just equality and functions. But I mean, there is one small example. So I'm saying that C is 21, and I'm saying that C has no factoring. So I'm saying for whatever O and P I pick that, and both are greater than 1, that then the multiple of O and P should be different than C. And of course, this whole thing is unsatisfiable, because if I plug in 3 and 7 into the quantifier, it just says 21 is different from C, and C is different from C is equal to 21. So this immediately false. However, there is no 3 and 7 in the formula anywhere, right? So so it's not, it gets trickier with theories, and plus there's issues with induction, right? So things that you need to prove with induction, they're also somewhat out of reach. Anyhow, this is a hard problem. So we know that quantifiers in SMT is hard. So we use this, we just pretend that we have no theories. And so this gives us an algorithm that really just does what I just described. So I have some ground part and the quantified part, and I'm just extending the ground part with terms that are coming from the ground part in every step, while G is satisfiable. Right. So as long as G is satisfiable, the moment it becomes unsatisfiable, I stop and I know the formula is unsatisfiable. In some strict sense, I should not call this an algorithm, because it's not guaranteed to stop, because I might never find the right substitution to make it unsatisfiable, in particular if it's satisfiable. But this comes with a problem, because typically things in SMT are undecidable. Okay, so this was just a kind of a taste of the theory that is behind the quantifiers in SMT. And so the takeaway message here is that I can just look at the terms that are currently in the formula and pick one of those terms and plug in it into the quantifier and continue. However, this choice is always going to be in some sense non-deterministic. So we're asking the question, can machine learning help us with this task, right? So if I have many terms that I can pick to plug in, which one should I choose? And this is what I've been working on most recently. So we're using the SMT solver CVC4, which is one of the state-of-the-art SMT solvers. Very nice to use, open source, GitHub, and everything, and supports a lot of theories. So very amenable to this kind of work. And I'm assuming that for each variable I have bunch of terms that I can plug in. Depending, this might depend on the type of the variable, etc. And then I'm assuming that I have some predictor that lets me sort the terms. And then I'm instantiating the tuples of these terms into the quantified variables. So I'm being a little bit vague here. So I mean, just to recap very quickly, I have a bunch of quantifiers, and each instantiation means substituting a tuple of terms. For each variable, I need to pick one term, right? And currently, I'm kind of ignoring that it's a tuple. I'm just looking for one order of terms for each. It would be also interesting to look at the tuples, but we're not doing that right now. So what is the machine learning that I'm using now? So we're just using bag of words, which is probably one of the simplest embedding of formulas, while ignoring names, of course, because we don't want to learn things that depend on names. So for instance, if I see the expression y plus x plus 3, I just see, oh, this is I have plus sign twice. I have 2 variables and 1 number. Yeah, so this is my feature. So it's my feature vector given a term. So it's a bit of a sparse feature vector, but reasonable. And when I'm looking at the candidates that may be substituted into the variable for the purpose of resolving the quantified problem, I just look at the quantifier and the term. I calculate the feature vectors and I concatenate them together, and this gives me a feature vector for the term. So, okay, I mean, there's different ways of doing this. Obviously, this is what we're doing right now, and we're just applying these boosted trees. There's this framework like GBM for doing the prediction, for the learning and prediction. Yeah, so this is nice because it's fairly quick, so I can run it from the solver, and I just ask for each term what is the prediction value, and then I sort the terms according to the prediction value. I know this might be a little bit vague. This part is not yet written up. We're in the process of writing it up. I don't know if there's any questions with respect to this.
So one thing that was not clear to me is how are you training the machine learning model here?
Oh yeah, so as I just solve one instance, and I look at the instantiations that were useful. Right. So if I go back to so essentially, assuming there's just one quantifier in the formula, there's more, but it doesn't matter. So the solver will try many tuples to instantiate these variables, right?
Yeah.
And some of these tuples were useful to disprove the formula, and some of them were just not useful. So I just have a 1-0 classification, right? Useful, not useful.
Okay. Yeah.
Of course, you could try to come up with something more fine-grained, but this is what we're using now. And one thing that we're using for that is that CVC4 now has some sort of a capability of producing a proof. So, this is an engineering problem, but you need to worry about it, of course, is that the solver just does many instantiations, but only some of them were really needed to disprove it. And we need to get this information out of the solver. So that part, fortunately, CVC4 does for us. Otherwise, we would have to somehow hammer it out.
Yeah, thanks.
Yeah, Pashutan is asking, one potential is that your model would only learn to mimic the solver's behavior. Yes, no. Might not learn a novel strategy. Well, okay. I mean, I think the short answer would be, well, any machine learning approach can overfit. So that that would be probably the short answer. The longer answer is that the features that we're using are extremely lossy, just to say. I mean, there's a lot of information lost, right? So I'm just looking at the term and the quantifier, and I'm not looking at the rest of the formula, and I'm just using it as a bag of words. So the model really has very little information about what is happening. Actually, this was one of the issues that we had at the beginning. I was using some shorter feature vectors, and I was just getting too many feature vectors that were exactly the same. So we had to grow it. Yeah, I mean, but of course you're right that we have a bit of a chicken and egg problem, that somehow the training samples are coming out of the solver, and then we're using it in the solver. I will show some experiments So I think it's not the case that to a degree, but to a degree it probably is happening. I'll just show very quickly some experiments that might shed some light on this. One thing is, actually, one thing that I should say with respect to this, even if we just improve the solver that it would find things faster, I think that would be good, right? So imagine that the solver is going to instantiate these all variables with zeros, and then with all ones and all twos and whatever, until it finds that plugging in all tens or all hundreds was useful, right? So it went through many of these unuseful ones, like all zeros, all ones, but in the end, I only needed this 100. And if I already was able to make the solver to come up with this 100 faster than before, it would still be interesting because I'm making the solver faster. That's a good question. I think it's non-trivial, but I think there's a lot of factors in the problem. So so some sort of preliminary results. So this is some class of problems that are coming from the UFLIA logic, which means that I have functions, uninterpreted functions, and linear integer arithmetic. And in this setup, we run the solver, and it solves some instances, and we learn from those, and we run the solver again on the instances that we have not solved. Yeah, so this is kind of this little bit this issue with that Pashutan is pointing to, that we're kind of learning what to do from the solver itself. However, we do get some improvement, right? So there is a spike of number of instances that the solver has solved at the beginning, and then then it plateaus, and we don't seem to be able to push it further. I think there's some more comment from Pashutan. I mean, you could definitely use some more advanced approaches. I mean, okay. So this is showing something. We're getting something, and this is a different scenario. So this is a kind of a funny experiment. So I ran the different types of logics. So I trained on a different logic and used it on another one. So I ran these benchmarks, from UFNIA, which is uninterpreted functions and nonlinear arithmetic. So I learned a model on those problems, and then I ran this learned model as a predictor on a different set of problems where there's no longer nonlinear problems, but only linear problems. And actually, it improved. So, I mean, this family has a lot of, let's say, easy problems, right? So this is 20 seconds. So there's nothing really happening until this 5,000 last 1,000 problems that we can solve. And you can see, you can see that the machine learning curve is slightly slower. So of course, so I'm calling the model. So I'm not learning anything. I'm just predicting, and prediction still cost me time, right? So even though it's these boosted trees, they are fairly fast. I still need to run them for many possible candidates, and so that it's a little bit slower, but not horribly. In the end, it surpasses the number of solved instances. So that was a kind of a pleasant surprise for me, that even if I learn on a very different set of problems, I can learn from that. And another thing that we were looking into, and this is also just being written up. So instead of using bag of words, we are looking into these graph neural networks, and we're not using it for quantifiers. So this is a little bit going outside of quantifiers, but it's still ML for logic. So the idea is that, you know, instead of having bag of words or whatever hand designed features, we use these modern graph neural networks. If you're not familiar with it, you know, it's roughly the idea is that I represent the formula as a graph, but I ignore the names, right? So I just say, you know, there's a constant, there's a variable, but I don't say what's the name of the variable. And then I'm learning certain it's called message passing, but essentially it's learning about some coefficients that should be used, how to aggregate neighbors of each node, and then there is one node that all the other nodes join into, and this gives me like kind of a result of the network. Yeah, I don't want to go into the details, but like it's this very complex, much more complex architecture, more expensive, of course, but the idea is that I don't need to come up with features, right? So rather than me as a designer coming up with features, somehow the model figures out the features on its own. So this is roughly the idea. And hopefully it will be smarter than me, right? And we have used this model for this portfolio prediction. So for the idea is that you have a number of solvers, and somebody gives you a formula, and you should pick which solver you should choose. And yeah, we're getting some fairly nice results. So you cannot get better than the virtual best solver, which is essentially the same thing as running all the solvers in parallel. All right, so there's no way how to surpass the virtual best solver using a portfolio, but we're getting fairly close, right? So the best solver is somewhere here, and the predictions are somewhere in between. This is one family of problems, Ufnia. We also tried some configurations of a single solver, right? So you might not have a portfolio of solvers, but the solver itself has a lot of configurations. Again, you know, this is the virtual best, and this is the prediction. We're particularly happy with this graph. So this is again the virtual best solver, and these are our predictions, and it's really tightly close to the virtual best. So I mean, so this is not about quantification per se, but it's somehow showing that these smart representations based on graph neural networks, or maybe on something else, but you can get some good performance, better performance than designing the features yourself. Okay, yeah. So this is the end, and just to quickly summarize. So I was trying to convince you today that we have found out that machine learning can help us with finite domains, so quantifiers of finite domains, and what was somewhat unusual is that we needed to learn objects, not just the prediction, right? So you cannot just get 3.7 out of the machine learning model. You need an actual object. And in terms of first-order logic, we have this improved Herbrand theorem that lets us just pick some terms that are currently available in the formula, which makes the problem more manageable. It's still undecidable, but we can algorithmically it's more manageable, and so we can train prediction on this finite set, and it seems that it's doing something, and the final comment that was that other than using these hand design features, you can also use this graph neural networks in formulas, and it might give you a better performance. Okay, so that's all for me, and happy to take more questions if there are any.
Thanks a lot, Mikoláš. So I'm doing the official applause on behalf of everybody. We certainly do have time for questions, although we did have a fair number of them already, but it's always nice to have more.
There's a question. Great talk. Thanks for the GNN's case. You just get the embedding once at the beginning and use that to choose the solver from the portfolio. No, I mean you have to construct the graph, right? So you have to like the embedding is kind of mysterious. So this goes against this. And one thing that I a little bit don't like about it is that it goes against this interpreted machine learning, right? So it's just a way how to get a set of features from a graph, right? So essentially, you need to take the formula, construct the graph, and evaluate the network on the graph, and that gives you the features then that you learn and that you use in some standard setting. Yeah, you do. Yeah, you have to always you always have to recreate the graph.
Any other questions or comments before we let go of Mikoláš? Again, just to put a reminder in the chat that people who can make it, who are in a nice enough time zone, are warmly welcome to come to Gathertown to the Simons Institute at Gathertown afterwards. But first, while we have Mikoláš here, we can ask more questions if there are any more questions.
You use only abstractions under approximation. Did you think to use also over approximations? Yeah, I've been somehow thinking about this at some point. So I know that this kind of work is very popular in, for instance, with loop invariant generation or invariant generation in software verification. So people do under approximation and over approximation. And I think I was thinking about it at some point and I was not able to conceptualize it. So somehow it was not making sense to me, or I couldn't make sense out of it. It's definitely an interesting question. How is it possible that in some counterexample guided approaches you can do under and over approximation, and here maybe not? Yeah, I don't have a good answer. It's definitely if someone has an answer to that, it would definitely be interesting.
So this question might be a little bit premature, but do you think there's any hope of not only getting improvements from ML, but sort of being able to interpret why ML is doing what it's doing and gain an understanding rather than just the black box magic improvements?
Yeah, I mean, so yeah, it's the whole field. It's kind of, it seems to me that it's, people are trying to have explainable AI, but explainable ML, but then the best approaches are less and less explainable. In some sense, what I'm doing is is maybe not so strange, right? Because maybe so the solver deals with formulas that are written by humans, and humans don't write arbitrary formulas, but they write some formulas that come from some problems and from some real world inspiration. So it's possible maybe that statistically I can learn somehow what people are writing in some sense, right? So so it's not such a black magic, but in the end, yeah, I agree. It's a little bit it's difficult. I mean, because all the simpler models. So we started with some simpler prediction models, and it was just not getting too much improvement, not really anything. So like these, so you have some very nice interpretable simple models, linear models, or logistic regression, or decision trees. So these things are fairly easy to interpret, but they have such a small prediction power that in the end they're hard to use.
So again, we've had the Simon's Institute GatherTown link in the chat now several times, so that you'll be able to find it. People who can are warmly welcome to come there. Any final questions for Mikoláš before we wrap up? And thank Mikoláš again for a great presentation.
Okay, thank you for having me. Yeah, so hope to see you all soon at some also non-virtual event. Okay.
Thank you so much.
Bye.